Welcome to section 4.5, Rational Functions, their asymptotes and discontinuities. At the end of this section, we should be able to answer these questions. How do we determine the end behavior of a rational function? What are the possible end behaviors of a rational function? What causes a rational function to be undefined at a particular value of x? What are the possible behaviors of the graph of a rational function at or near these values of x? How do we determine which of these behaviors will occur at or near these values of x? To determine the end behavior of a rational function, we need to perform an analysis which I like to call the Great Battle. Remember that a rational function is defined as a polynomial divided by a polynomial. And what we are going to do is we are going to compare the degree of the polynomial in the numerator with the degree of the polynomial in the denominator. So we will look at the degree of the numerator versus the degree of the denominator. And we have three possible outcomes. A proper rational algebraic expression is defined as a situation. Let's undo that. It's defined as a situation where the degree of the numerator is less than the degree of the denominator, in which case I like to define that as a situation where the bottom wins. The denominator has a larger degree. Improper rational algebraic expressions have two possibilities. First, the degree of the numerator is equal to the degree of the denominator, in which case I declare a tie, or the degree of the numerator is greater than the degree of the denominator, in which case the top wins. We'll take a look at all three of these cases and how they will affect the end behavior of a rational algebraic expression. Let's take a look first at proper rational algebraic expressions. And that's defined as when the degree of the numerator is less than the degree of the denominator. So let's create a nice proper algebraic expression. Let's try with x over x squared plus 1, where the degree of the numerator is 1 and the degree of the denominator is 2. So the denominator has a greater degree than the degree of the numerator. So let's see what happens as x gets larger and larger to this function. So I'm going to first put the function into my y equals. So x divided by the quantity x squared plus 1. Close that off. And then we're going to go back to our home screen. And now I'm going to input various values of x to see what happens as x increases. So I'm going to call up my y variables, function y1, and let's see what happens when we put 10 into our function. We get 10 over 101. Okay, so that's about 0.1. Let's try a larger number for x here. We call that. Let's put another 0 in. So find out what happens to our function when x is 100. Okay, we get 0.00999. Seems to be getting smaller. And if we try one more 0 in there, we can see that we get an even smaller number. And that makes sense. If we go back to our original expression, we can see that as x here, we start putting in numbers for x, it gets pretty large, but x squared gets even larger. And eventually the difference between them is so great that the ratio becomes a number very, very close to 0. So what we will say here is that our end behavior, in this case where the degree of the numerator is less than the degree of the denominator, or the bottom wins, as x increases in a positive or negative fashion, approaches plus or minus infinity, the graph of the expression will approach 0. All right, so that makes sense. If you think about putting in negative numbers instead of positive, you can try that on your own. You'll see that the numbers also get smaller and smaller. They'll just be negative, but getting closer and closer to zero. This is a lot of words to describe what happens. We actually have some notation, shorthand, for what's going on here. And what we say is that for this function f of x, which is defined as a polynomial over a polynomial, where the degree of the numerator is less than the degree of the denominator, we use this notation here to describe it. We say the limit of the function, or of the y values, as x approaches infinity, the limit of the y values is 0. Our expectation is that this function will trend towards 0. Let's take a look at a second case, where the degree of the numerator is equal to the degree of the denominator. And in our great battle lingo, we say that that's a tie. So let's come up with an equation where the degree of the numerator is equal to the degree of the denominator. So how about something like x cubed over, or let's make it 4x cubed, over 2x cubed plus 3x plus 1. All right, so let's plug this into our calculator here. Call it up. Let's go back to y equals, clear out this, and we are going to put in 4x cubed. 4x cubed. And then we're going to divide that by the quantity 2x cubed plus 3x plus 1. X cubed plus 3x plus 1. And whoops, I guess I wasn't paying attention there. 2x cubed. Let's get rid of all of that. And get down from there. Plus 3x. Close it off. And go back to our home screen. And we'll try these same ideas here. Let's go back up and ask for y1 of 10. And what do we get? We get 4,000 over 2,031. All right, so that's a reasonable fraction, I guess. And let's see what happens as we ask for something a little larger here. y1 of 100. And here we go. 1.99996. So a number that seems to be getting close to 2. Let's try going a little larger. y1 of 1,000. And we get even closer to 2. So I think it would be a reasonable assumption to say that our function is approaching 2 as our y values get larger. Let's see what happens when our x values are negative. So let's go back to the 10 here. But let's change that to a negative 10. So minus 10. And when we ask for that, we get again 4,000 over 2,029, which makes sense because if we look at our numerator, we'll end up cubing the negative 10, so that will be a negative number. And then if we look at our denominator, we'll be cubing the negative 10 again, so we'll have another negative number there. And a negative over a negative leaves me a positive. So let's just make sure that we're seeing the same trend on the negative side. So we'll change this 100 to negative 100. Back here, second delete, negative. And we try it out. And again, we get this positive number getting closer and closer to 2. So if we look at our original function over here, we notice that our leading term here, or the term with the highest degree in both of these, both the numerator and the denominator. So we have a 4x cubed and a 2x cubed. And in the long run, these are the terms that are going to be the most important as x gets larger and larger. Because if you compare a value of x cubed to a value of 3x, the x cubed is going to be so much larger as x gets larger and larger. Think of 1,000 cubed being close to a billion, whereas 3 times 1,000 is only 3,000. You compare a billion to 1,000, and that 1,000 becomes pretty insignificant. So what we ultimately end up doing is comparing the leading terms here, the degree of the numerator, the 4x cubed and the 2x cubed, and we simplify. Okay. And that simplifies. The x cubes are going to cancel out, and we end up with a 2 in our simplified expression, which is where we saw the function approaching. So what we're going to say here then is that in this case, as x increases in a positive or negative fashion, approaches plus or minus infinity, the graph of the expression will approach a horizontal asymptote determined by the ratio of the coefficients of the leading terms of the numerator and denominator. Let's just verify that by looking at the graph itself. So I'm going to do a zoom standard here, so zoom 6, and we can see that while we may have some interesting things going on here in the middle, as we go out towards the outside, our graph approaches a value of 2. Once again, we have some notation to describe this phenomenon where our end behavior has a horizontal asymptote that results from the ratio of the leading terms. And here's how we say it. For the function f of x, where f of x is a rational function, where the degree of the numerator equals the degree of the denominator, then the limit as x approaches infinity here of our function, so the expectation for the y values of our function, ends up being the leading coefficient of the numerator divided by the leading coefficient of the denominator. Let's look at our third and final case of end behavior for the improper rational algebraic expressions, where the degree of the numerator is greater than the degree of the denominator. So let's look at a case where let's create one here. How about x to the 5th plus 2x squared plus 1 all over x cubed? And here we can see, let's just define this as f. Let's plug this into our calculator and see what's going to happen. And we will get in a sense pretty quickly, I think. Let's go in, change to y equals, clear that out. Parentheses, x to the 5th plus 2x squared. So x raised to the 5th plus 2x squared plus 1. And all divided by x cubed. Okay. Now let's try some values here. Let's see. Throw 10 in there. We're going to get a number, wow, 100,201 divided by 1,000. Let's try something a little bit larger. A little bit, let's make it 100. So actually a lot larger. And we get 10,000. Now let's try one more here. Get a 0. Wow, 1 million. By increasing by a factor of 10, we increased by a factor of 100 there. Interesting. We can see that the graph is just going to get larger and larger. And if you look at how y1 of 100 compared to y1 of 1,000, it did increase by increasing by a factor of 10. It actually increased our y values by a factor of almost 100, or 10 squared. And that's not a coincidence. To find out what's going to happen here, again, we can look at our function and actually do the long division that this rational function implies by the fraction. So let's do a little long division here. X cubed into let's see, x to the fifth plus, okay, there's no fourth or third term, so 0x to the fourth plus 0x cubed plus 2x squared plus 0x plus 1. And we're going to divide this function here. So x to the third goes into x to the fifth, x squared times. And we multiply that back, x to the fifth, and we subtract, and we get 0 here, and 0 here, and 0 here, and 2x squared here. Now x cubed doesn't go into 2x squared, so 2x squared is our remainder, which we could write as a mixed fraction. We also can bring down the 1. So our mixed fraction for this long division would be 2x squared plus 1 over x cubed. Now here we have a new way of describing this polynomial. This is a simplified form of our original, and we can see that our trailing term here, the 2x squared plus 1 over x cubed, actually falls into that situation where the degree of the denominator is greater than the degree of the numerator, which means in the long run this term essentially becomes 0, and our graph looks more and more like the graph of x squared. If we wanted to summarize that in words, we could, undo that. Say that the end behavior, as x increases in a positive or negative fashion, of this type of expression where the degree of the numerator is greater than the degree of the denominator, will approach a non-vertical asymptote, which means that it will start looking a lot like some other function. So in this case, it will be mimicking the behavior of the polynomial piece of the improper rational algebraic expression when we rewrite it as a mixed rational algebraic expression, or a polynomial plus a proper rational algebraic expression. So that last piece that we came up with, the x squared plus 2x squared plus 1 over x cubed, is a mixed rational algebraic expression. And here, what that means is that eventually our graph will look more and more like x squared. Now, we find that mixed rational algebraic expression by actually performing the long division implied by that original fraction. So we divide the denominator into the numerator, and everything except that final remainder term becomes the function that our original expression will eventually resemble.